So hello everyone and welcome to NEETOPEDIA, that is NEETka Encyclopedia. And today we'll be starting with Group 14 elements. We had already finished Group 13 elements in the previous audiobook. Please note that these audiobooks of P block element will be coming group wise right from Group 13 to Group 18. Okay, so let's get started. 11.5 Group 14 elements, the carbon family. Carbon, silicon, germanium, tin, lead and Florovium are members of Group 14. Carbon is the 17th most abundant element by mass in the Earth's crust. It is widely distributed in nature in free as well as in combined state. In elemental state, it is available as coal, graphite and diamond. However, in combined state, it is present as metal carbonates, hydrocarbons and carbon dioxide gas in air. One can emphatically say that carbon is the most versatile element in the world. Its combination with other elements such as trihydrogen. Organic chemistry is devoted to carbon-containing compounds. It is a naturally occurring carbon, contains two stable isotopes, carbon-12 and carbon-13. In addition to this, third isotope C14 is also present. It is a radioactive isotope with half-life of 5770 years and is used for radiocarbon dating. Silicon is the second most abundant element on Earth's crust and is present in nature in the form of silica and silicates. Silicon is a very important component of ceramics, glass and cement. Germanium exists only in traces. Tin occurs mainly as cassiterite SnO2 and lead as galena PbS. Florovium is synthetically prepared radioactive element. Ultra-pure form of germanium and silicon are used to make transistors and semiconductor devices. Symbol of Florovium is Fl. Its atomic number 114, atomic mass 289 gram per mole and electronic configuration radon 5F14 6D10 7s2 7p2. It has been prepared only in small amount. Its half-life is short and its chemistry has not been established yet. The important atomic and physical properties, including their atomic configuration of the elements of Group 14 living Florovium, are given in Table 11.3. Some of the atomic, physical and chemical properties are discussed below. 11.5.1 Electronic configuration. The valence shell electronic configuration of these elements is Ns2 and P2. The inner core of the electronic configuration of elements in this group also differs. 11.5.2 Covalent Radius. There is a considerable increase in covalent radius from carbon to silicon. Thereafter, from silicon to lead, a small increase in radius is observed. This is due to the presence of completely filled d and f orbitals in heavier members. 11.5.3 Ionization enthalpy. The first ionization enthalpy of Group 14 members is higher than the corresponding members of Group 13. The influence of inner core electrons is visible here also. In general, the ionization enthalpy decreases down the group. Small decrease in ionization enthalpy from silicon to germanium to tin and slightly increase in from tin to lead is the consequence of poor shielding effect. 11.5.4 Electronegativity. Due to small size, the elements of this group are slightly more electronegative than Group 13 elements. The electronegative values for elements from silicon to lead are almost same. 11.5.5 Physical properties. All members of Group 14 are solids. Carbon and silicon are non-metals. Germanium is a metalloid, whereas tin and lead are soft metals with low melting points. Melting points and boiling points of Group 14 elements are much higher than those corresponding to elements of Group 13. 11.5.6 Chemical properties. Oxidation states and trends in chemical reactivity. The Group 14 elements have 4 electrons in the outermost shell. The common oxidation states exhibited by these elements are +4 and +2. Carbon also exhibits negative oxidation states. Since the sum of first 4 ionization enthalpy is very high, compounded +4 oxidation states are generally covalent in nature. In heavier members, the tendency to show +2 oxidation state increases in the sequence germanium is less than, tin is less than lead. This is due to the inability of NS2 electrons of valence shell to participate in bonding. The relative stabilities of these two oxidation states vary down the group. Carbon and silicon mostly show +4 oxidation state. Germanium forms stable compounds in +4 state and only few compounds in +2 state. Tin forms compound in both oxidation states. Tin in +2 state is a reducing agent. Lead compounds in +2 state are stable and in +4 state are strong oxidizing agents. In tetravalent state, the number of electrons around the central atom in a molecule is 8. Being electron-precise molecules, they are normally not expected to act as electron acceptor or electron donor species. Although carbon cannot exceed its covalent more than 4, other elements of the group can do so. It is because of the presence of d orbital in them. Due to this, their halides undergo hydrolysis and have tendency to form complexes by accepting electron pairs from donor species. For example, species like SiF6 2-, GeCl6(2-), SNOH6(2) exist where the hybridization of the central atom is sp3d2. Number 1. Reactivity towards oxygen. All members when heated in oxygen form oxides. There are mainly two types of oxides, that is, for formula MO and MO2 respectively. SiO only exists at high temperature. Besides, oxide in higher oxidation states of elements are generally more acidic than those in lower oxidation states. The dioxides, carbon dioxide, silicon dioxide and germanium dioxides are acidic, whereas SnO2 and PbO2 are amphoteric in nature. Among monoxide, CO is neutral, GeO is distinctly acidic, whereas SnO and PbO are amphoteric. Problem 11.5. Select the members of group 14 that form the most acidic dioxide, is commonly found in +2 state and is used as semiconductor. Solution. Number 1. Carbon. Number 2. Reactivity towards water. Carbon, silicon and germanium are not affected by water. Tin decomposes steam to form dioxide and dihydrogen gas. Lead is unaffected by water, probably because of the protective oxide film formation. Number 3. Reactivity towards halogen. These elements can form halides of formula MX2 and MX4. Except carbon, all other members react directly with halogen under suitable condition to make halides. Most of the MX4 are covalent in nature. The central metal atom in these halides undergo sp3 hybridization and the molecule is tetrahedral in shape. Exceptions are SnF4 and PbF4, which are ionic in nature. PbI4 does not exist because PbI bond initially formed during the reaction does not release enough energy to unpair 6s2 electrons and excite one of them to higher orbital to have 4 unpaired electrons around lead atom. Heavier members, germanium to lead, are able to make halides of formula MX2. Stability of dihalides increases down the group, considering the therm easily hydrolyzed by water because of the central atom can accommodate the lone pair of electrons from oxygen atom of water molecule in d orbital. Hydrolysis can be understood by taking example of SiCl4. It undergoes hydrolysis by initially accepting lone pair of electrons from water molecules in d orbitals of silicon and finally leading to the formation of SiOH4 as shown below. Problem 11.6. SiF6(2-) is known whereas SiCl6(2-) is not. Give possible reasons. Solution. The main reasons are: number 1, 6 large chloride ions cannot be accommodated around Si4+ due to limitation of its size. Number 2, interaction between lone pair of chloride ion and Si4+ ion is not very strong. 11.6. Important trends and anomalous behaviors of carbon. Like first member of other groups, carbon also differs from rest of the members of its group. It is due to its smaller size, high electronegativity, high ionization enthalpy and unavailability of d orbitals. In carbon, only S and p orbitals are available for bonding, and therefore it can accommodate only 4 pairs of electrons around it. This would limit the maximum covalence to 4, whereas other members can expand their covalence due to presence of d orbitals. Carbon also has unique ability to form p-pi multiple bond with itself and other atoms of small size and high electronegativity. Few examples of multiple bonding are C double bond C, C triple bond C, C double bond O, C double bond S, and C triple bond N. Heavier elements do not form p-pi bond because of their atomic orbitals are too large and diffuse to have effective overlapping. Carbon atoms have tendency to link with one another through covalent bonds and form chains and rings. This property is called catenation. This is because the CC bonds are very strong. Down the group, the size increases and electronegativity decreases, and thereby tendency to show catenation decreases. This can be clearly seen from the bond enthalpy values. The order of catenation is very much high in carbon, continued by silicon greater than germanium, which is almost equal to 10. Lead does not show catenation. Due to the property of catenation and p-pi bond formation, carbon is able to show allotropic forms. 11.7 Allotropes of carbon. Carbon exhibits many allotropic forms, both crystalline as well as amorphous. Diamond and graphite are two well-known crystalline forms of carbon. In 1985, third form of carbon known as fullerenes was discovered by H. W. Croteau, E. Smalley, and R. F. Kurl for his discovery, where they were awarded Nobel Prize in 1996. 11.7.1 Diamond. It has a crystalline lattice. In diamond, each carbon atom undergoes sp3 hybridization and linked to other 4 carbon atoms by using hybridized orbitals in tetrahedral fashion. The CC bond length is 154 picometer. The structure extends in space and produces a rigid 3-dimensional network of carbon atoms. In this structure, 11.3 directional covalent bonds are present throughout the lattice. It is very difficult to break extend covalent bonding, and therefore diamond is the hardest substance on the earth. It is used as an abrasive for sharpening hard tools, in making dyes, and in manufacture of tungsten filament for electric light bulbs. Problem 11.7. Diamond is covalent, yet it has high melting point. Why? Solution. Diamond has 3-dimensional network involving strong carbon-carbon bonds which are very difficult to break and in turn has high melting point. 11.7.2 Graphite. Graphite has layered structure. The layers are held by van der Waals forces and distance between 2 layers is 340 picometer. Each layer is composed of planar hexagonal rings of carbon atoms. Carbon-carbon bond length within the layer is 141.5 picometer. Each carbon atom in hexagonal ring undergoes sp2 hybridization and makes 3 sigma bonds with 3 neighboring carbon atoms. Fourth electron form a pi bond. The electrons are delocalized over the whole sheet. Electrons are mobile and therefore graphite conducts electricity along the sheet. Graphite cleaves easily between the layers and therefore it is very soft and slippery. For this reason, graphite is used as dry lubricant in machines running at high temperature where oil cannot be used as a lubricant. 11.7.3 Fullerenes. Fullerenes are made by heating of graphite in an electric arc in presence of inert gases such as helium or argon. The sooty material formed by condensation of vaporized CN small molecules consisting of mainly C20 with smaller quantity of C70 and traces of fullerenes consisting of even number of carbon atoms up to 350 or above. Fullerenes are the only pure form of carbon because they have smooth structure without having dangling bonds. Fullerenes are cage-like molecules. C60 molecule has the shape of soccer ball and is called Buckminster fullerenes. It contains 26 membered rings and 12 5-membered rings. A 6-membered ring is fused with 6 or 5-membered rings, but a 5-membered ring can only fuse with 6-membered ring. All the carbon atoms are equal and undergo sp2 hybridization. Each carbon atom forms 3 sigma bonds with other 3 carbon atoms. The remaining electron at each carbon is delocalized in molecular orbitals, which in turn gives aromatic character to the molecule. This ball-shaped molecule has 60 vertices and each one is occupied by 1 carbon atom. It also contains both single and double bonds with carbon-carbon distances of 143.5 picometer and 138.3 picometer respectively. Spherical fullerenes are also called buckyballs in short. It is very important to know that graphite is thermodynamically most stable allotrope of carbon, and therefore Teleshnev formation of graphite is taken as 0. The enthalpy of formation values of diamond and fullerene C60 are 1.90 and 38.1 kJ per mole respectively. Other forms of elemental carbon like carbon black, coke and charcoal are all impure forms of graphite or fullerenes. Carbon black is obtained by burning hydrocarbons in a limited supply of air. Charcoal and coke are obtained by heating wood or coal respectively at high temperatures in absence of air. 11.7.4 Uses of carbon. Graphite fibers embedded in plastic material form high tensile strength, lightweight composite. The composites are used in products such as tennis racket, fishing rod, aircraft and canoes. Being good conductor, graphite is used for electrodes in batteries and industrial electrolysis. Crucibles made from graphite are inert to dilute acids and alkali. Being highly porous, activated charcoal is used in absorbing poisonous gases, also used in water filters to remove organic contaminators and in air conditioning system to control odor. Carbon black is used as black pigment in black ink and as filler in automobile tires. Coke is used as a fuel and largely as a reducing agent in metallurgy. Diamond is a precious stone and is used in jewelry. It is measured in carats, where 1 carat is equal to 200 milligram. 11.8 Some important compounds of carbon and silicon. Oxides of carbon. 2 important oxides of carbon are carbon monoxide and carbon dioxide. 11.8.1 Carbon monoxide. Direct oxidation of carbon in limited supply of oxygen or air yields carbon monoxide. On a small scale, pure carbon monoxide is prepared by dehydration of formic acid with concentrated H2SO4 at 373 Kelvin. On commercial scale, it is prepared by passage of steam over hot coke. The mixture of CO and H2 thus produced is known as water gas or synthesis gas. When air is used instead of steam, a mixture of CO and N2 is produced, which is called producer gas. Water gas and producer gas are very important industrial fuels. Carbon monoxide in water gas or producer gas can undergo further combustion, forming carbon dioxide with liberation of heat. Carbon monoxide is a colorless, odorless and almost water-insoluble gas. It is a powerful reducing agent and reduces almost all metal oxides other than those of the alkali and alkaline earth metals, aluminium and few transition metals. This property of carbon monoxide is used in extraction of many metals from their metal oxide ores. In carbon monoxide molecule, there is 1 sigma and 2 pi bonds between carbon and oxygen. Because of the presence of a lone pair on carbon, CO molecule acts as donor and reacts with certain metals when heated to form metal carbonyls. The highly poisonous nature of CO arises because of its ability to form a complex with hemoglobin, which is about 300 times more stable than the oxygen hemoglobin complex. This prevents hemoglobin in the red blood corpuscle from carrying oxygen around the body and ultimately resulting in death. 11.8.2 Carbon dioxide. It is prepared by complete combustion of carbon and carbon-containing fuels in excess of air. In laboratory, it is conveniently prepared by action of dilute HCl on calcium carbonate. On commercial scale, it is obtained by heating limestone. It is a colorless and odorless gas. Its low solubility in water makes it of immense biochemical and geochemical importance. With water, it forms carbonic acid H2CO3, which is a weak diabasic acid and dissociates in 2 steps. H2CO3 or bicarbonate ion buffer system helps us to maintain pH of blood between 7.26 to 7.42. Being acidic in nature, it combines with alkalis to form metal carbonates. Carbon dioxide, which is normally present to the extent of 0.03% by volume in the atmosphere, it is removed from it by the process known as photosynthesis. It is the process by which green plants convert atmospheric CO2 into carbohydrates such as glucose. The overall chemical change can be expressed as 6CO2 plus 12H2O in the presence of light and chlorophyll gives C6H12O6 plus 6CO2 plus 6H2O. By this process, plants make food for themselves as well as for animals and human beings. Unlike CO, it is not poisonous, but the increase in combustion of fossil fuels and decomposition of limestone for cement manufacture in recent years seem to increase the CO2 content of the atmosphere. This may lead to increase in greenhouse effect and thus raise the temperature of atmosphere, which might have serious consequences. Carbon dioxide can be obtained as a solid in the form of dry ice by allowing the liquefied CO2 to expand rapidly. Dry ice is used as a refrigerant for ice cream and frozen food. Gaseous CO2 is extensively used to carbonate soft drinks. Being heavy and non-supporter of combustion, it is used as fire extinguisher. A substantial amount of CO2 is used to manufacture urea. In CO2 molecule, carbon atom undergoes sp hybridization. The 2 sp hybridized orbitals of carbon atom overlap with 2 p orbitals of oxygen atom to make 2 sigma bonds, while the other 2 electrons of carbon atom are involved in p-pi bonding with oxygen atom. This results in linear shape with no dipole moment. The resonance structure as shown below. 11.8.3 Silicon dioxide SiO2. 95% of the Earth crust is made up of silica and silicates. Silicon dioxide, commonly known as silica, occurs in several crystallographic forms. Quartz, cristobalite, and tridymite are some common crystalline forms of silica, and they are interconvertible at suitable temperature. Silicon dioxide is a covalent three-dimensional network solid in which each silicon atom is covalently bonded in a tetrahedral manner to 4 oxygen atoms. Each oxygen atom in turn is covalently bonded to another silicon atom as shown in the diagram. Each corner is shared with another tetrahedron. The entire crystal may be considered as a giant molecule in which 8-membered rings are formed with alternate silicon and oxygen atoms. Silica in normal form is almost non-reactive because of its high silicon-oxygen bond enthalpy. It resists the attack by halogens, dihydrogen, and most of the acid and metals even at elevated temperatures. However, it is attacked by HF and NaOH. Quartz is extensively used as piezoelectric material. It has made possible to develop extremely accurate clocks, modern radio and television broadcasting, and mobile radio communication. Silica gel is used as a drying agent and as a support for chromatographic materials and catalyst. Kieselguhr, an amorphous form of silica, is used in filtration plants. 11.8.4 Silicons. There are a group of organosilicon polymers which have R2SiO as a repeating unit. The starting materials for the manufacture of silicons are alkyl or aryl substituted silicon chlorides, where R is alkyl or aryl group. When metal chloride reacts with silicon in presence of copper as catalyst at a temperature of 573 Kelvin, various types of methyl substituted chlorosilicane of formula MeSiCl3, Me2SiCl2, Me3SiCl with small amount of Me4Si are formed. Hydrolysis of dimethyl dichlorosilicane, that is CH3 whole twice CiSiCl2, are followed by condensation polymerization yields straight chain polymers, that is 2CH3Cl plus Si in the presence of copper powder at 570 Kelvin gives CH3 whole twice SiCl2, which on hydrolysis gives CH3 whole twice SiOH whole twice. The chain length of the polymer can be controlled by adding CH3 whole 3 SiCl, which blocks as the ends as shown below. Silicons, being surrounded by non-polar alkyl groups, are water-repelling in nature. They have in general high thermal stability, high dielectric strength, and resistance to oxidation and chemicals. They have wide applications. They are used as sealant, greases, electrical insulators, and for waterproofing of fabrics. Being biocompatible, they are also used in surgical and cosmetic plants. Problem 11.8. What are silicons? Solution. Simple silicon consists of SiO whole end chains in which alkyl or phenyl groups occupy the remaining bonding positions on each silicon. They are hydrophobic in nature. 11.8.5 Silicates. A large number of silicate minerals exist in nature. Some of the examples are feldspar, zeolites, mica, and asbestos. The basic structural unit of silicates is SiO4-4, in which silicon atom is bonded to 4 oxygen atoms in tetrahedron fashion. In silicates, either the discrete unit is present or a number of such units are joined together via corners by sharing 1, 2, 3 or 4 oxygen atoms per silicate units. When silicate units are linked together, they form chain, ring, sheet or 3-dimensional structures. The negative charge on silicate structure is neutralized by positive charged metal ions. If all the 4 corners are shared with other tetrahedron units, 3-dimensional network is formed. 2 important man-made silicates are glass and cement. 11.8.6 Zeolites. If aluminium atoms replaced with few silicon atoms in 3-dimensional network of silicon dioxide, overall structure is known as aluminium silicate and requires a negative charge. Cations such as sodium, potassium or calcium balance the negative charge. Examples are feldspar and zeolites. Zeolites are widely used as catalysts in petrochemical industries for cracking of hydrocarbons and isomerization. Example, ZSM-5, a type of zeolite, is used to convert alcohols directly into gasoline. Hydrated zeolites are used as ion exchangers in softening of hard water. Summary. P block of the periodic table is unique in terms of having all types of elements: metals, non-metals and metalloids. There are 6 groups of P block elements in periodic table, numbering from 13 to 18. Their valence shell electronic configuration is ns2 np126. Differences in the inner core of electronic configuration is greatly influenced in their physical and chemical properties. As a consequence of this, a lot variation in properties among these elements is observed. In addition to the group oxidation state, these elements show another oxidation states differing from the total number of valence electrons by unit of 2. While the group oxidation state is the most stable for the lighter elements of the group, lower oxidation states become progressively more stable, thus considerably influences the ability of these elements to form pi bonds. While lighter elements form p-pi-p-pi bonds, the heavier ones form d-pi-p-pi or d-pi-d-pi bonds. Absence of d orbital in second period elements limits their maximum covalence to 4, while heavier elements can exceed this limit. Boron is a typical non-metal and other members are metals. Availability of 3 valence electrons for covalent bond formation using 4 orbitals leads to so-called electron deficiency in boron compounds. This deficiency makes them good electron acceptor and thus boron compounds behave as Lewis acid. Boron form covalent molecular compounds with dihydrogen as boranes, the simplest of which is diborane B2H6. Diborane contains 2 bridging hydrogen atoms between 2 boron atoms. These bridge bonds are considered to be 3-center 2-electron bonds. The important compounds of boron with dioxygen are boric acid and borax. Boric acid, BOH whole thrice, is a weak monobasic acid. It acts as a Lewis acid. Selenium exhibits +3 oxidation state with heavier elements. +1 oxidation state gets progressively stabilized on going down the group. This is a consequence of the so-called inert pair effect. Carbon is a typical nonmetal forming covalent bonds employing all its 4 valence electrons. It shows property of catenation, the ability to form chains or rings, not only with carbon-carbon single bond but also with multiple bonds. The tendency to catenation decreases as carbon is much greater than silicon, is greater than germanium, which is almost equal to tin, and is greater than lead. The carbon provides one of the best examples of allotropy. The 3 important allotropes of carbon are diamond, graphite, and fullerenes. The members of carbon family mainly exhibit +4 and +2 oxidation states. Compounds in +4 oxidation states are generally covalent in nature. The tendency to show +2 oxidation state increases among heavier elements. Lead in +2 state is stable, whereas +4 oxidation state is a strong oxidizing agent. Carbon also exhibits negative, whereas oxidation state, it forms 2 important oxides, CO and CO2. Carbon monoxide is neutral, whereas CO2 is acidic in nature. Carbon monoxide, having lone pair of electrons on C, forms metal carbonides. It is deadly poisonous due to higher stability of its hemoglobin complex as compared to that of oxyhemoglobin complex. Carbon dioxide as such is not toxic, however, increased content of CO2 in atmosphere due to combustion of fossil fuels and decomposition of limestone is feared to cause increase in greenhouse effect. This in turn raises the temperature of the atmosphere and causes serious complications. Silica, silicates and silicons are important class of compounds and find applications in industry and technology. So that's the end of it. Thank you for listening to this audiobook, and please subscribe to the channel and stay tuned for more such content.